All right. Good morning, everybody, to this not sunny Monday, but the start of a new week where we will hopefully do something that you find slightly new and exciting. We have a very slow start to things in this course. Even though it is a calculus course, we take the first couple of weeks to just ease into things, remember the key things we need to remember. Because in the past, we have tried just starting with the new material and assuming people would go and review what they need to review, and it has always been disastrous. So now we take a couple of weeks, show, highlight what you absolutely need to remember, and have moving forward into the new material, and then there is no excuse, hopefully, when things get a little bit new and because of that, more interesting. Okay, so what have we done? What have we done? Well, we haven't done much. We have talked about linear functions. You looked at some word problems with linear functions, and that's pretty much it. So let us move on to topic 1D, of course, in my numbering system, and that'll be on quadratic functions. Certainly the next step forward. Now, let's look at our first, what I'll call basic function. The linear functions are the y equals mx plus b. It's a little different. Uh, the most familiar out of all of them, and I don't really group them in with the more complicated functions. This will be our first one, our first basic function. And over time, we're going to make a little library in our heads of all these basic functions that we can use to build more complicated functions. This is going to be our first one. Again, not very complicated. But the first time you saw it, you maybe made a little table of x and y values, maybe a -2 for x, -1, 0, 1, 2. And then we, of course, this is a function. We plug in the x value, we get a y value out, and the obvious y values are just the x values squared. And then we can have a little graph. Again, this is a review, so I'm not dwelling on this for too long, but definitely something we want to remember. And we get a very nice parabola shape that has a symmetry mirrored in the y-axis. Now, for some reason, I really struggle to draw on this because I look at my screen and I don't look at my hand. So if my parabola looks a little wobbly, this is in fact a single solid line, even though it doesn't always look like it. For some reason, the left side is really hard for me to angle and draw. Not that I should make excuses, I should be able to do this perfectly. But I do it in little bits so that the curvature is nice. And we have our 0, 0 at the bottom here. Uh, Now the x and y axes are not to scale. If I, not the same scale. If I plug in a 1, I'll get a 1 there. If I plug in a 2, I'll get 4 from that and -2. So I have these points, and of course there's a bunch of them in between. All right, so I have my parabola. All right, that should look fairly familiar. Sorry, that's not a -4, it's just a dotted line. All right, and I can have many more points. It's defined for any x value. Uh, I can plug in any x value, square it, and I'll get a y value. All right, pretty straightforward stuff, if assuming we remember. Let me just make some space here. I don't need the y-axis to be that long at the bottom. Okay. Now what we're going to do first is modify this basic function to create other functions that are based on this parabola shape, this quadratic function. So let's just have an example. I don't have a problem for this. Actually, I do have a problem, but I'll do it in a second. Let's look at y equals x squared plus 1 and understand how I can find or build this new function from my basic function. Well, let's scroll up a little bit. If I take this basic function I have in my library and see what happens to it in its function form, I see that, well, the original right-hand side, which was x squared, is still there. I just add 1 every time to get the y value in this new function. So that means that if I'm at x equal to 0, originally 0 squared gives me a y value of 0. I'm doing the same thing, and then I'm adding 1, so I'm going to get a y value of 1. If I'm at x equal to 1, originally it was 1 squared. Now it's 1 squared again, and then I add 1, so it's going to sit a little higher at 2. And the same thing is going to happen at when x is negative 1. So the point in my basic function's graph essentially just moves up by 1 unit. I have the same shape, wobbly as it may be. This left side is the bane of my existence, getting it nice and smooth. Everything is just shifting up by 1. So I can get the graph of this new function by understanding how it was transformed from the basic function. So there is the function transformation, so M here, transformation, which is y equal to x squared changes to y equal to x squared plus 1. In brackets, the right-hand side stays the same, but plus or minus some number. Then there's a corresponding change in the graph because the function changed. So then I have a graph transformation, which is a vertical shift, I'll call it. Fancier word is translation, but I'm shifting it up and down. Now, as we go, we'll see that a function transformation like this might always give me a similar graph transformation. And for different things I do to the function, different but consistently so, different things are going to happen to the graph. But it's very important to understand the function changes, and that has a result in the graph. Okay. People do this backwards. They just want to manipulate the graph, but the function changes, and then based on how that changes, the graph might change in a specific predictable way. So if we do problem, let me make a new page here. I'll look at problem problem 1.6, number 1, where I have given f of x equals x squared plus 2. Let me go back here, see the question. RHS stands for right hand side. I have a left side of the function, I have a right side of the function. The right hand side between or from the basic to the new function, the right hand side changed. And depending on how that changed, the graph changes in a predictable way. So if I take my original, add or subtract a number to the right hand side, the graph is going to shift up and down. Right hand side. Okay, so let's read the question. 6.1, number 1. Graph the quadratic function. Find the x and y intercepts of each graph, if any exist. It's given in what we'll talk about the forms in a second, and I have a transformation from my basic function, which is how I figure it out. I'm going to talk about the next bit in a second. So first of all, I start. Now I'm doing it for this uh, admittedly very simple transformation in a lot of detail. Uh, but this is the simplest transformation, which is why it's the first one. Uh, Not all of them will be that straightforward, perhaps. So I'm going to start with my basic function, which is y equals x squared, and I'll draw the graph at the bottom here. Doesn't have to be big. Label parabola. Ooh, that was nice. That was a nice smooth parabola. But this other side is going to be a mess. Oh, it's not bad. I'm going to take it. I like to draw my parabolas a little wider than they actually are. It just makes it easier to draw, and the scale on the x and y axes don't have to be the same. I then go and change the function by adding 2 to the right hand side. That has a resulting change in the graph. Now I know there are some people sitting there like, why is he making such a big deal of a vertical shift? Well, because later on it's not going to be that easy perhaps, and there are traps that I can easily fall into without realizing it if I don't approach this in a specific way. Because I added 2 to the right hand side of the original, that means the parabola is, oops, a little wobbly, is shifted up by, whoa, see the left hand side, it's a disaster. Now it's on video and I'll never live this down. I try and make it a little bit go slower, but it's at least the right curvature by 2 units. And I have my reference point here, which is the lowest point. We call that the vertex, the turning point, if you will, and the vertex now sits over there. New vertex. And because I changed the function in a specific way, the graph changes in a predictable way. Just erase this extra long y-axis again. All right. So they want to know the y-intercept. Easy. Because I just moved my graph up, the y-intercept is 0, 2. X-intercept, of course, because of what I did, there aren't any. The vertex is this turning point. In the case of the basic parabola, it's the lowest point. It's the point 0, 2 as well. And The line of symmetry here that cuts this in half, creating this mirror image on either side, is called the axis of symmetry, which in this case is the line x equal to 0. The y-axis is the line x equal to 0. Now, as we move this graph a little bit more, you'll see the line a little bit more, but for now, it's the symmetry line. We're sitting right on the vertex. All right. So nothing too major. If we change the function in a specific way, the change in the graph is predictable. And our first one is a vertical shift. I want to do 1.8. Just make a new page first. I want to do problem 1.8 as well. Problem 1.8, number 1. Number 1. Because while we're talking about quadratic functions, I want to notice how I'm not really depending on the x squared aspect. That if I take a function, y equals f of x, could be anything. If I keep that right-hand side the same and add 3, for example, the result in the graph is the same. So let me update it over here. If I take any function, not necessarily x squared, but I change the function in the same way by adding or subtracting a number, then a vertical shift of whatever that graph was is still what's happening. Now, of course, because I had a different function, I might not know what the graph looks like, but whatever that shape was is going to shift vertically. Up if I added, down if I subtracted. So now I have some function. I don't even know what the function is. Given some function, I can't graph it. I don't know what it is. They only tell me that there's a point 2, negative 3 on the graph. So point 2, negative 3. So if I want, I could visualize this over here. I don't know exactly the specifics of the function, but I can sort of visualize it. Now the point 2, negative 3 is going to sit over here somewhere, right? 2 for x, negative 3 for y. So I don't know what it is, right? It could be all kinds of stuff happening. Who knows what this graph is? I'm guessing. But I'm changing the function to the same right-hand side, and then I'm adding 3. Then the graph changes in a predictable way, which is that everything shifts up by 3. So this point that I know a little bit about now shifts vertically up because I added 3 by 3 units. So that point is now going to sit over here at 2, 0. And the same graph shape is happening. Oops. I don't know what it is, right? It could be anything. Same shape. Everything shifts up. It's a vertical shift up because I added 3. Now let me just check. Suppose I have a point. Find a point on the graph of the given transformed function. So my new point is then obviously to 0 because everything shifted up. So as I'm looking at the quadratic function, it's familiar, easy-ish. I notice how The transformations that I perform on this can be used on any function. The graph might just look different, but what happens to the graph doesn't change. It's always, if I do something to the function, then there may be a predictable change in the graph as well. All right, so let's look at how else we can change the function so that the graph is predictable. So I'm going to change, let's do it, I'm just going to rearrange my spacing here. So let's look at y equals, which one do I want to do next? I'm pretty sure. Let me just check this one. X minus 2, everything squared. Now the function has changed from my basic function, which is y equals x squared, to my transformed function, y equals x minus 2 squared. So I know what the basic graph looks like. Let's draw it. It's my basic parabola. Whee! That side is so easy to draw. This side, so much harder. That's good enough. I have my vertex here. Maybe I want to keep track of another point, maybe 1, 1. That should be good enough. Okay, so now I'm trying to understand, instead of me just telling you, I want to understand why the graph changes in the way that it does. So let me just set up my XY plane here. Like so. All right. So now, what is happening to the graph? Well, when I look at this bottom vertex point, in the original, I had to plug in x equal to 0 to find the corresponding y value of 0. So in the basic original, an x value of 0 gives me the answer for y, 0. What x value in the new function do I have to plug in order to get y equal to 0 now? That's my question. I didn't say it was a hard question, but it's nice to be involved. In the new case, I have to plug in a 2 for x if I want to get a y equal to 0 again, right? So let's put 1 over here and 2 over there. I'm running out of space. I need to do this again. I'm too close to the edge. I apologize. I'm just going to redo it and shift it a little bit. Just so I have some space to move here. So let's make that a 1. Let's make that a 2. And maybe I need some more points. Okay, that's a 2. Okay. So now if I plug in x equal to 2, I'm going to get a y value of 0. Now let's look at on the basic function, on the basic graph, this point 1, 1. If I wanted a y value of 1, among other things, I would have had to plug in x equal to 1. If I want in the new graph, in the new function, a y value of 1, I'm going to have to plug in a 3, because 3 minus 2 is 1, 1 squared is 1. So in order for me to get that y value of 1, I'm going to have to plug in a 3 for x. And of course, you can argue the other side. I can also, in the basic, plug in a negative 1. Now I'm going to have to plug in a 1 to get another y value of 1. And I can keep going with this argument and we'll see that the parabola is now sitting wobbly as it is over here like that. It's the same shape, but it's now shifted horizontally. It's a horizontal shift. How did I change the function? Because that still happened first. Now, many people would just casually say, oh, I subtracted 2 from x. It's not quite clear enough to say it like that so that it works for other more complicated functions as well. The transformation that I want to see here is I replaced in the original, I took x, took it out. In its place, I put in x minus 2. It's a replacement transformation. And if I think about it as a replacement transformation, it's going to keep me much safer and away from errors that I might not realize exist. So let's just highlight or summarize what is happening here. So my function transforms with a function transformation y equals x squared to y equals x minus 2 squared, for example. That is a replacement of x with x minus 2 in this case. Excuse me. The corresponding graph transformation is a horizontal shift to the right by, of course, 2 units. So a couple of things here. It's a little, maybe counterintuitive for some, that even though it was a subtraction, x minus 2, I shifted to the right. I shifted in the positive x direction. Now I remember still, I just had to make a mental note that it's opposite to what I might think. When I looked at the vertical shift, adding a number meant moving up the y-axis, moving up vertically. Now, subtracting moves me up along the x-axis. So it's not quite the same. So I have to be aware of that. If I replaced x with an x plus 2, then I would shift to the left. So it's maybe a little opposite to what you might immediately intuitively think. But we argued why it shifts to the right, so it definitely does. That, and I have this replacement transformation that regardless of how complicated this function originally might be, if I take out where the x is and I put in an x plus or minus a number, and that's all I do, then there is a predictable horizontal shift in the graph. Okay. So let us just do, I think I have a little example problem. I do not. We just did one, so it's fine. That is not the reason. It's only because you are working with the square function that it might look like that. My function is just an example. We could have any function, and then we don't have that square anymore. What happens horizontally is still the same. Let me write that out. I just use the quadratic function as a simple, familiar, specific function I can sort of look at. It's not dependent on the function at all. Wow, that was ugly writing. Whew. Let's just do better than that. That's not much better. Problem 1.8, what do I want to do here? I want to do number 2, where, yeah, I look at the y equals x squared, but I'm not really stuck to it in any way. I'm given a function y equals f of x and a point. Is it the same point? Whoop, yep, I'm right there. 2, -3, 2, -3. Yeah, I don't want to, I mean, I do want to look at a specific example to make it a little bit more relatable with what you know, but I don't want to make any general conclusions based on that specific x squared example. It has properties that functions in general won't have. So here just have a function. Don't know what it is. In number 2, I want to evaluate. So let's say it like this to make it consistent with the other one. I start with my function. Let's just see that function before we transform it. I can't draw apparently. Wow, where is my y-axis? No, there it is. That looks ugly now. There we go. Not sure why that didn't want to draw. I don't know what it looks like, but I know the point 2, -3 is on it. I don't know. I'm just drawing a random line, right? Don't know what it looks like. No idea. They don't need to tell me. If I had a function I've seen before, yeah, then I can graph it. But it's independent of what the function is. I then transform that to a new function, but it's changed in a specific way. Wherever the x is gets replaced with an x plus 3. So that is replacing x with x plus 3. And our function notation makes that uh, easy to illustrate. Regardless of the function, instead of x being the input, x plus 3 is the input. That's exactly the replacing idea. So let's give ourselves some space here and see what happens. Now, it's a little bit more abstract than the argument than working with a specific y equals x squared, but nothing changes. Uh, when I do this replacement transformation, what happens to the graph is a horizontal shift, the same argument as for the parabola. Let's not say. Okay, let's say by 3 units. And because it's x plus 3, I'm going to go left this time. So instead of the point being 2, -3, 3 units to the left, we'll have it sit at -1, -3. And this same shape, whatever that was, wobbly, let's try and repeat it, now sits over here. That's all I know. I don't know more about the function, right? But whatever shape I had originally, everything is preserved, just shifted to the left. So I have a different, very different transformation. But if that is what is how the function is changed, then the graph changes in a predictable way. It's just a different way. All right. So now I can just want to see if I can now put these together. Let's just do a quick little example to show which way we're headed here. I don't see a problem exactly like that. No, I'm gonna have to make one up, but that's not a problem. Um, let's suppose now we want to graph y equals x minus 1 squared plus 2. I'm keeping it simple. I don't know. Now I'm going to make a chain of transformations that I start with my basic function that this is built on, y equals x squared. That then changes to y equals x minus 1, everything squared, where what I'm doing is replacing x with an x minus 1, and that then changes from this middle function to the end result by taking the right-hand side. See, right-hand side is exactly the same, and then adding 2. Because I've taken the right-hand side and just added 2, that is another predictable graph shift. Okay, we just string them all together. So let's have little graphs here. Let me set it up first. So when the function comes from, or when the function is more complicated, I can see it as a sequence of transformations, one after another, so that I can keep track of how the graph changes from the basic wobbly parabola that I know and love. So I have my familiar parabola shape because that's the function I start with. The function changes first, in this case with a replacement of x by x minus 1. That means the original graph shifts to the right by 1 unit. Then another transformation from this current version to the new one is a change, keeping the right-hand side the same, adding a 2 to that whole right-hand side. That corresponds to a vertical shift up by 2, whoops, that was a little pointy, by 2 units. Wobbliness. And my vertex sits over there. So the more transformations we have, up to a point, we don't want to get crazy with it, we can create more complicated functions with a sequence of these transformations. And we can find the graph as well by just doing one at a time. All right. Okay, so we are building more complicated functions, but they're built on our familiar basic function. Now, eventually, we'll have more basic functions than just y equals x squared. Right now, I'm just using this one, and we'll build a good number of them in the end. But nothing's going to change. If my starting point changes, the starting graph changes, but how it is transformed doesn't change. Okay, so I want to see more transformations. Let's at least introduce a couple more to give us a little more room to move and see some variety in our examples. Next, I want to look at, which one do I want to do next? Let's say y equals 2 times x squared. Again, it's built on my basic function, x squared. And then I'm transforming it in some way to make the new function 2 times x squared. All right, now I know my basic function, so I know the graph. Again, some of these things are familiar. X squared, of course, very familiar, parabola. Uh, and slowly we're introducing new things or new ways of looking at things, ways that you might not be super used to. Oh, that's not a good parabola. Can I not get better? For some reason, you can draw 1,000 parabolas. They don't really get better. at least in my case. I have to sort of draw them systematically. Ah, that's not a bad one. It's the best I have. Now, what is happening to the graph? Let me set it up. Well, the argument's very similar. Let's look at this 0, 0 point. In the original, to get a y value of 0, I needed to plug in x equal to 0. That doesn't change in this case. To get a y value of 0, I still need an x value of 0. Great. That point has not moved at all. Let's get some other points here. 1, 1, maybe a 2, 4. Let's take the 1, 1 point. And that might be enough. To get, in the original, a y value of 1, my x value needed to be 1 on the right side. Now to get a y value, well, let me phrase it differently. Now when x is equal to 1, I'm going to do the same thing I did originally. The right-hand side is still there, but then it's multiplied by 2. So now I'm going to sit higher up. I've doubled my y value to 2. If I look at what happens at x equal to 2 originally, 2 squared, right-hand side, is still there, and then I double it. So it's going to be even higher. Let's say 8 sits over here. And the same thing happens on the left. So what I get, oh, that's not actually the best point there. Let me just fix that before we continue. So what I get is the graph is much steeper because the y values are doubled. And I get a sort of a stretched out, say 2 is over here for that point, a stretched out parabola. It looks a little jagged so that I can get that shape nice, right? And even then it's wobbly. Good job, me. Bad job. So it looks like a vertical stretch in the graph. It's stretched out vertically by doubling this right-hand side. So what happens is I took the same right-hand side and I multiplied it by 2. Now, of course, you can see it, or you can very quickly, hopefully, think that if I took a fraction, like a half, then all the y values would be reduced by a factor, all the same, and I get a vertical compression. So let's summarize it over here. So if I have a function transformation that is, let's say I have y equal to right-hand side. Actually, no, let's not do that. I have some function, right? We're not married to this x squared. It could be any function. Who cares? And then I am going to multiply it by some positive number. Could be a small little fraction. Could be a large number. What happens to the graph? How it, oh, that was a big S. How it transforms is by way of a vertical stretch or a compression, depending on the size of the number that's multiplied. So we use the basic parabola quadratic function as a starting point to help us understand why these things are happening to the graph when I change the function in a certain way, but I'm not really attached to that function, and it can be any function. It can be any function. So I'm not going to do all of the problems 1.8, but you can see problem 1.8 number 5 is very similar, that I'm taking the original and I'm multiplying by 3. I'm pretty sure you can handle those on your own. As long as I understand that different things I do to the function, that has different results in how the graph changes. But you'll notice it's always function first, graph is a result of that. Now let's look at y equals negative x squared. I like to separate the sign from the number I multiply in front. And we'll see why in a second. So we're going to start, of course, with our basic familiar parabola. Let's see it. So that it's not too abstract, there's my parabola, and I need the drawing practice anyway, which clearly does not help me. Ooh, maybe it's okay. Sort of. I don't like how it seems to turn back there. Let's see if I can fix that. It needs to curve up all the time. And I have some points there, maybe a 1. That was supposed to be a 1. Point there, 1, 1. That's good enough. Now, I'm going to look at my new function, y equals negative x squared. And its graph. Set it up. All right. Now, when x is 0, I got a y value of 0. To get a y value of 0 in this new case, x is still going to have to be 0. So that point doesn't change, vertex doesn't change. To get a y value of 1, that happened when x was 1. But now when x is 1, I'm going to have the same right-hand side, but I'm going to multiply that by negative 1. So that's just going to move that point to the bottom over here. And over here, this point, when I plug in negative 1, I get the same right-hand side, but then I multiply that by negative 1. So I'm going to get the point negative 1 instead of 1. So the y value size is the same. It's just negative. So my parabola is going to be pointing down in some wobbly way. So bad at drawing. There you go. So the graph is experiencing, I'll call it a vertical reflection. Uh, some people say it's a reflection in the x-axis. That's true. It's great. But I'm focusing on the vertical aspect of the reflection. I had to flip it vertically. What happened to the function? How did the function change? It was negative 1 times the right-hand side. Right-hand side stays the same, negative 1 times that right-hand side. Okay. Let's just summarize that. Function, we have a minute left, so we will soon pause and then just continue this tomorrow. And there's some stuff to do the day after, and then we'll let this quadratic function topic show us everything we need to see for now. So if I have my function, could be x squared, could be something else, I don't know, and that changes to the same but negative, then my graph transforms by way of a vertical reflection. Now, the reason I call it a vertical reflection and not a reflection in the x-axis, though you or welcome to. If I look back, we have a lot of tabs open here. Very first one. When I changed the right-hand side by adding or subtracting a number to it, it was a vertical shift. When I took the right-hand side of the function and multiplied it by a positive number, it was a vertical stretch or compression. When I take the right-hand side and multiply it by -1, it's again a vertical transformation. Different transformations, but it's all vertically done. It's all vertical. When I take the right-hand side and I do something to it, depending on what I do, something happens to the graph, but it's always vertical, vertical, which is why I want to help myself remember that by calling it a vertical reflection. So, um, there's not much to do for you right now. If you want to look at some problems, you can definitely look at 1.8 if you want to, but you don't have to. We now want to just string these together in a longer sequence of transformations before moving on. What you can do, I would suggest you do, is just take a page and just summarize these transformations like this, like we did here. But see them all uh, just sort of written out. See the big picture of all the transformations we have available to us so far. And that'll get you ready for uh, just making a sequence and stringing them all together in an example that we can do tomorrow because we are out of time. Are there any questions at this stage? Sometimes our discussion is a little bigger and we need to sort of let it roll over to the next day, but we have the time. There is no need to worry. So our topic isn't done. Don't look at the problems and think, oh, I need to be able to do all of these, where our discussion is only halfway. So we'll finish the rest tomorrow. Any questions or comments at this stage? This is review, but I will admit that, different instructors for pre-calculus, some focus on transformations, some never do any transformations. So I can't really call it review. The further we go, the less reviewy it becomes, and it could be brand new to some. Uh, but technically, it is review. That it is still in our first test. Yes, still on the first test. The website says what topics are covered in which test. So we just have a very slow start to the calculus, but it is all still very important. Look at the topics if you want to know what we're going to be doing. Everything is there. And if it's not on that list, we're not doing it. Simple as that. Simple as that. There are more, in, let's say, more involved, fuller calculus classes. And that's not what our aim is here, because this is sort of the level we need for the life sciences and things like that. It's a little less. All our topics are on the course website. We are going to string these transformations together. And we certainly have to do a couple of examples that we can see a bigger situation. But because we're out of time, we'll have to wait for tomorrow to do a nice sequence of transformations. Yes. Sorry, you asked sequences. That's a completely different topic. We're going to make a sequence of transformations. Yes. And we're going to do that tomorrow. All right. Until tomorrow, feel free to use Discord, ask questions. In the meantime, maybe your fellow student can see it, maybe I'll see it, or we'll just pick it up tomorrow. Until then.